Hello there, and welcome to Sleepy Science. If you love exploring impossible questions and discovering how science can solve the most extreme challenges, you're going to want to subscribe. Because every episode, we dive deep into fascinating scientific adventures. Tonight's journey is no exception. We're going to Mars, and we're going to see if science can save you when everything goes wrong. Before we begin tonight's journey, I want to remind you why we're here. Science isn't just facts in textbooks. It's not just equations on a board. Science is a way of understanding the world, a way of solving problems, a tool that humans have used for thousands of years to explore, to discover, to survive. And tonight, we're going to see science in action, in the most extreme situation imaginable, because tonight, you're going to Mars, and you're going to need every bit of science you know to survive. Imagine this. You're an astronaut, you've trained for years, you've studied, you've prepared, you've traveled millions of miles through space, you've landed on Mars, the red planet, the fourth planet from the sun, the next frontier for humanity. But something goes wrong, your ship crashes, you're alive but you're alone, your crew is gone. Your communication is damaged, your supplies are limited, Earth is millions of miles away, help might not come for years, or maybe never. What do you do? How do you survive? How do you turn this impossible situation into a chance to live? The answer is science. Chemistry, physics, biology. All working together. All keeping you alive. One day at a time. Mars is beautiful. It has canyons deeper than the Grand Canyon, mountains taller than Mount Everest, sunsets that paint the sky in blue. But Mars is also deadly. The air is poison. The cold can freeze you solid. The radiation can kill you slowly. There's no water you can drink. No food you can eat. No air you can breathe. But here's the thing. You have something powerful, you have science, you understand chemistry, you know physics. You've studied biology, and science might just save your life. Tonight we're going on an incredible survival adventure. We'll explore how chemistry can turn Martian ice into water you can drink. We'll discover how physics can help you create breathable air from poison gas. We'll see how biology can help you grow food in soil that wants to kill plants. We'll learn how all of science works together to keep you alive. This isn't just a story. This is real science. Everything we'll explore is based on actual research, on real Mars missions, on what scientists are planning right now for future Mars colonies. The science is real, the challenge is real, the survival, that's up to you. So get comfortable, close your eyes if you want. Let's imagine you're stranded on Mars. And let's see if science can save you. Chapter 1. The Martian Environment. Understanding your enemy. You step out of your crashed ship. Your spacesuit is working, for now. You look around. Mars stretches out before you in shades of red and orange and brown. The sky is pinkish during the day, dark blue at sunset. Rocks are scattered everywhere. Dust covers everything. In the distance you can see mountains, craters, ancient riverbeds that dried up billions of years ago. You're not the first to see this view. Robotic explorers have been here before you. Since 1965, when Mariner 4 flew by Mars and took the first close-up photos. Those 22 grainy black and white images shocked scientists. They showed a cratered, moon-like surface. Not the canals that some had imagined. Not the signs of life people had hoped for. Just a dead, barren world. Since 1971, when Mariner 9 became the first spacecraft to orbit another planet, it revealed volcanoes, canyons, ancient river valleys. Evidence that Mars wasn't always dead, that it had a past, a history, a story to tell. Since 1976, when Viking 1 and Viking 2 landed on the surface, the first successful landings on Mars, they conducted experiments, searched for life, found none. But they taught us about the soil, the atmosphere, the conditions, everything we needed to know to plan future missions. Since then, many more have come. Pathfinder, with its little rover Sojourner, Spirit and Opportunity, the twin rovers that were supposed to last 90 days. Opportunity lasted over 14 years. Traveled 28 miles, sent back over 200,000 images, changed everything we knew about Mars. Phoenix dug into the soil, found water ice. Curiosity drilled into rocks, found evidence of ancient lakes. Insight listened to Marsquakes, mapped the planet's interior. Perseverance is collecting samples, planning to bring them back to Earth. Ingenuity became the first aircraft to fly on another planet. Each mission teaching us more. Each one revealing secrets. Each one preparing the way for humans. For you. But you're the first human, the first to set foot on Mars, the first to see this view with your own eyes. Not through cameras, not through screens, but directly in person. It's historic, it's amazing, it's terrifying. It's beautiful, but it wants to kill you. Mars is like Earth's cold, dry cousin. It's smaller than Earth, about half the size. A day on Mars is almost the same as a day on Earth. 24 hours and 37 minutes. But a year on Mars, that's almost twice as long as an Earth year. 687 days. Mars is farther from the Sun than Earth, about 1.5 times farther. That means it gets less sunlight, less warmth. About 43% as much solar energy as Earth receives, but that's just the beginning of your problems. Mars also has dust, lots of it. Fine powdery dust that gets everywhere. It's made of iron oxide, rust. That's why Mars looks red. The dust is red, it covers everything. And it can be a problem. It can clog filters, it can scratch surfaces, it can get into equipment, it can cause problems you haven't even thought of yet. Mars has massive dust storms. Global dust storms. That can cover the entire planet. Last for weeks. Or months. During these storms, the sky turns dark. Red. Dusty. Sunlight can't reach the surface. Solar panels stop working. Temperatures drop. Everything becomes harder, more dangerous. The Opportunity rover was killed by a dust storm in 2018. A global storm covered Mars. Blocked sunlight. The rover's solar panels couldn't charge. Its batteries ran out. It went silent. Never recovered. That's how dangerous dust storms can be. The storm started in May 2018 as a small dust storm in the Acidalia Planitia region, but it grew quickly. By June, it was a regional storm, covering thousands of square miles. By late June, it became global, covering the entire planet. The sky turned dark, red, dusty. Sunlight couldn't reach the surface. Opportunity tried to survive. It went into a low-power mode, shut down non-essential systems, tried to conserve energy. But the storm lasted too long. Weeks. The rover's batteries drained completely. It went silent. NASA tried to contact it. For months. Sent over 1,000 commands. But no response. The mission was declared over in February 2019, after 15 years of operation, killed by a dust storm. But dust storms also have benefits. They redistribute dust, clean some areas, cover others. They can reveal things, hidden features, new resources. They're part of Mars's weather, part of its environment. You need to understand them, Prepare for them, survive them. But dust storms also have benefits. They redistribute dust, clean some areas, cover others. They can reveal things, hidden features, new resources. They're part of Mars's weather, part of its environment. You need to understand them, prepare for them, survive them. Dust is also electrostatically charged. It sticks to things, to spacesuits, to equipment, to solar panels. It's hard to remove, hard to clean. You'll spend a lot of time dealing with dust, cleaning it, removing it, trying to keep things working despite it. It's a constant challenge, a constant problem. But it's part of surviving on Mars. Mars has seasons too, like Earth, because Mars tilts on its axis, about 25 degrees. Similar to Earth's 23.5 degrees. So Mars has spring, summer, fall, and winter. But each season lasts about twice as long as on Earth. Because a Martian year is almost twice as long. During Martian winter, near the poles, temperatures can drop even lower, to -200 degrees Fahrenheit or colder. And carbon dioxide freezes out of the atmosphere, forms dry ice on the ground. During summer, it sublimates, turns back into gas. This creates seasonal changes, wind patterns, weather systems, even though the weather is nothing like Earth's. Mars also has the largest volcano in the solar system, Olympus Mons. It's about 13.6 miles high. That's 3 times taller than Mount Everest. It's so massive that if you stood on its peak you wouldn't be able to see the base. The horizon would curve away. But Olympus Mons is dormant. It hasn't erupted in millions of years, maybe billions. Scientists think Olympus Mons formed because Mars doesn't have plate tectonics. On Earth, tectonic plates move. Volcanoes form, then move away from their magma source. They stop growing. But on Mars, the crust doesn't move. So when a volcano forms, it stays in place. It keeps growing for millions of years, until it becomes massive, until it becomes Olympus Mons. Mars has the largest canyon system too, Valles Marineris. It's about 2,500 miles long, up to 4 miles deep. If it were on Earth, it would stretch across the United States, from New York to Los Angeles. It's a massive scar on the planet's surface, evidence of Mars's violent past. Scientists think Valles Marineris formed when the Tharsis region bulged upward, creating stress in the crust, causing it to crack, to split, to form this massive canyon. It's not like the Grand Canyon, which was carved by water. Valles Marineris was formed by geological forces, by the planet itself, stretching, cracking, breaking apart. These features are amazing, they're beautiful, they're evidence of Mars's history. But they're also dangerous. The canyons are deep, the volcanoes are massive. If you're near them, you need to be careful. The terrain is rough, the slopes are steep, navigation is difficult. But they also might provide resources, minerals, water ice, protection from radiation. So they're both a challenge and an opportunity. But you're not here to sightsee, you're here to survive. And survival starts with understanding what you're up against. Let's start with the air, or rather, the lack of it. On Earth, you breathe air that's mostly nitrogen, about 78%. Oxygen makes up about 21%. That oxygen is what your body needs. Your lungs take it in. Your blood carries it to every cell. Your cells use it to make energy. Without oxygen, you die in minutes. Mars has an atmosphere, but it's nothing like Earth's. Mars's atmosphere is 95% carbon dioxide. Carbon dioxide is what you breathe out, it's what plants use. But you can't breathe it in, your body doesn't work that way. Mars has only 0.13% oxygen. That's almost nothing. If you tried to breathe Martian air, you'd suffocate in seconds. Your body would panic, your lungs would burn, you'd pass out, and then you'd die. But that's not the only problem. Mars's atmosphere is thin. Really thin. On Earth, the air pressure at sea level is about 14.7 pounds per square inch. That's like having a small car pressing on every square inch of your body. You don't feel it because your body is used to it. Your insides push back with equal pressure. On Mars, the air pressure is less than 1% of Earth's. It's about 0.095 pounds per square inch. That's incredibly thin. It's like being on top of Mount Everest, but 10 times higher, or more. What happens to your body in low pressure? Bad things. The water in your body would start to boil. Not because it's hot, because the pressure is so low. Your blood would bubble. Your saliva would boil in your mouth, your eyes would feel like they're being pulled out. Your eardrums would rupture, your body would expand, and then it wouldn't be good. This is why you need a spacesuit. A spacesuit keeps pressure around your body, it keeps you alive. But spacesuits have limits. They can tear, they can leak, they need power, they need maintenance, and you're alone. With limited supplies. The thin atmosphere also means Mars can't hold heat. On Earth, our thick atmosphere acts like a blanket. It traps heat from the sun. It keeps temperatures relatively stable, not too hot, not too cold. Mars has no such blanket. During the day, near the equator, Mars can reach about 70 degrees Fahrenheit. That's actually comfortable, like a nice spring day. But at night, the temperature plummets. It can drop to negative 195 degrees Fahrenheit. That's colder than dry ice. Colder than liquid nitrogen. Cold enough to freeze you solid in minutes. These temperature swings happen every single day, day after day, week after week. Your spacesuit has heaters, but heaters need power, and power is limited. If your heaters fail, you freeze. If you're outside at night without protection, you die. How do Mars rovers survive these temperatures? They have special systems. The Curiosity rover, which landed on Mars in 2012, uses something called a radioisotope thermoelectric generator. It's basically a nuclear battery. It produces heat from radioactive decay. That heat keeps the rover's electronics warm, even during the coldest Martian nights. But you probably don't have a nuclear battery. You have solar panels maybe, some batteries, limited fuel. You'll need to be creative. You'll need to understand how heat works, how insulation works, how to conserve energy. And then there's radiation. This might be the most dangerous threat of all. Earth is protected from radiation by two things. First, our thick atmosphere blocks a lot of it. Second, and more importantly, Earth has a magnetic field. Our planet's core is made of spinning liquid metal. This creates a magnetic field that extends far into space. This magnetic field deflects dangerous radiation, cosmic rays, solar flares, high-energy particles from the sun and beyond. Mars has no magnetic field. Not anymore. Scientists think Mars had 1 billion years ago. But Mars is smaller than Earth. Its core cooled faster. The liquid metal stopped spinning. The magnetic field disappeared. And without that protection, radiation pours down onto Mars's surface. The Curiosity rover measured this radiation. It found that radiation levels on Mars are about 2.5 times higher than what astronauts experience on the International Space Station. And the space station is already dangerous. Astronauts there are exposed to radiation that increases their cancer risk. Curiosity's Radiation Assessment Detector, or RAD, has been measuring radiation since 2012. It's found that a person on Mars would receive about 0.67 millisieverts per day. That's about the same as getting a chest X-ray every day. Over a year, that's about 245 millisieverts. Over a mission of 500 days, that's about 335 millisieverts. That's significant. It increases cancer risk. It's something you'd need to protect against. The radiation comes from two main sources: galactic cosmic rays, high-energy particles from outside our solar system, and solar particle events, bursts of radiation from the Sun during solar flares, or coronal mass ejections. These events can be especially dangerous. They can deliver a large dose of radiation in a short time. You'd need to take shelter, wait them out, protect yourself. On Mars, without protection, you'd be exposed to even more. Over time, this radiation would damage your cells. It would increase your risk of cancer. It would weaken your immune system. It would cause other health problems. If you stayed on Mars for years without proper shielding, the radiation could kill you. How do you protect yourself? You need thick walls. Water is good at blocking radiation. So is soil. So is metal. You'd need to build underground, or cover your habitat with thick layers of material. But building takes time, takes resources, takes energy. So Mars wants to kill you in three main ways. The thin, poisonous atmosphere wants to suffocate you. The extreme cold wants to freeze you. The radiation wants to slowly poison you. And that's just the environment. We haven't even talked about food, or water, or the mental challenge of being alone. But here's the thing: understanding these dangers is the first step to surviving them. You know what you're up against. You know what you need to solve. And science can help you solve every single problem. Before we dive into solutions, let's understand one more thing about Mars. Why is it like this? Why did Mars lose its atmosphere? Why is it so different from Earth? Billions of years ago, Mars might have been more like Earth. It might have had a thicker atmosphere, liquid water on its surface, maybe even life. But something happened. Mars changed. It became the cold, dry planet we see today. Scientists think Mars lost its magnetic field first. Without that magnetic field, the solar wind could reach the atmosphere. The solar wind is a stream of charged particles from the Sun, protons, electrons, moving at incredible speeds, hundreds of miles per second. It's constantly blowing through space, like a cosmic wind, but made of particles, not air. On Earth, our magnetic field deflects it, acts like a shield, protects us. The solar wind flows around our planet, like water around a rock in a stream. Our atmosphere stays safe, protected, intact. But on Mars, without protection, the solar wind hit the atmosphere directly, stripped away molecules, one by one. Over billions of years. The process is called atmospheric escape. And it's still happening today. NASA's MAVEN spacecraft has measured it, watching as Mars's atmosphere slowly leaks away into space. About 100 grams per second. That doesn't sound like much. But over millions of years, it adds up. Over billions of years, it destroyed Mars's atmosphere. Scientists estimate that Mars once had an atmosphere about as thick as Earth's, maybe thicker. But now it's less than 1%, almost gone. And it's still shrinking, slowly, steadily. Mars is still losing its atmosphere, even today. As the atmosphere thinned, Mars couldn't hold heat, temperatures dropped, water froze, or evaporated into space. The planet became cold, dry, dead. At least on the surface, but Mars wasn't always like this. Evidence suggests it was once warmer, wetter, more like Earth. There are dried up riverbeds, lake beds, even evidence of ancient oceans. The Curiosity rover found rounded pebbles, like those in Earth's rivers, formed by flowing water. The Perseverance rover is exploring an ancient river delta, where a river once flowed into a lake, billions of years ago. What happened? Why did Mars change? Scientists think several things. The loss of the magnetic field was key. But also, Mars is smaller than Earth. It cooled faster. Its geological activity slowed. Volcanoes stopped erupting. The planet's interior cooled. Without geological activity, there was no way to replenish the atmosphere, no way to add new gases. So once the atmosphere was stripped away, it was gone. Forever. But water might still exist underground, in aquifers, in ice deposits, protected from the harsh surface conditions. And that's where your survival story begins. Because water is the key to everything. Without water you die in days. With water, you can survive for weeks. And with science, you might be able to make water on Mars. But finding water is just the beginning. You need to extract it, purify it, store it, use it efficiently, recycle it, create a sustainable system. And that's where chemistry comes in. Chemistry is the science of matter, how substances interact, how they transform, how you can use those transformations to survive. Chapter 2. Making water. Chemistry saves your life. Water is life. Your body is about 60% water. Your brain is even more. About 75%. Every cell in your body needs water. Your blood is mostly water. Your muscles need water. Your organs need water. Without water, you die in about 3 days. Maybe 4 if you're lucky. But water is more than just something you drink. It's a chemical, H2O. 2 hydrogen atoms bonded to 1 oxygen atom. It's one of the most important molecules in the universe. And it has unique properties. Properties that make life possible. Water is a solvent. It dissolves things. That's why it can carry nutrients through your body. Why it can transport waste. Why it's so useful. So essential. Water has a high heat capacity. It can absorb a lot of heat before its temperature changes. That's why oceans moderate Earth's climate. Why your body can maintain a stable temperature. Why water is so important for regulating heat. Water expands when it freezes. Most substances contract. But water expands. That's why ice floats. Why frozen pipes burst. But it's also why life can exist under ice. Why lakes don't freeze solid. Why fish can survive in winter. Water is polar. The oxygen atom pulls electrons toward itself, creates a slight negative charge. The hydrogen atoms have a slight positive charge. This polarity makes water molecules stick together, creates surface tension, allows water to climb up narrow tubes, to flow against gravity, to do amazing things. Understanding water's chemistry helps you understand how to work with it, how to extract it, how to purify it, how to use it, how to survive. On Earth, water is everywhere. It falls from the sky, it flows in rivers, it fills oceans. You can turn on a tap and get clean, safe water. But on Mars, there are no rivers, no oceans, no taps. But Mars does have water, just not in a form you can use right away. Scientists have known for a long time that Mars has water ice. They've seen it at the poles. Massive ice caps made of water and carbon dioxide ice. The North Polar Cap is about 600 miles across. The South Polar Cap is smaller, about 250 miles across. But those are far away. You probably didn't crash near the poles. You're probably somewhere near the equator, where it's warmer, where landing is easier. But scientists have also found evidence of water in other places. Using radar, using spectrometers, instruments that can detect water from orbit, they've found large deposits of water ice, buried underground, in mid-latitudes, not just at the poles. Some of these deposits are massive, hundreds of feet thick, miles across. They're like underground glaciers, frozen water, waiting to be discovered. In 2018, scientists using radar found what might be a large lake under the South Polar ice cap. about a mile below the surface, about 12 miles across. If it's real, it would be liquid water, not ice. But that's still being debated. More research is needed. But even if you're not near a big ice deposit, you can still find water. The Phoenix lander found it just inches below the surface. In 2008, Phoenix dug a trench, about 7 inches deep, and it hit ice, hard white ice, right there, in the soil. So water is accessible, if you know where to look, if you know how to extract it. But even near the equator, Mars has water. It's hidden in the soil, mixed with dirt and rocks, frozen solid. In 2008, a spacecraft called Phoenix landed near Mars's North Pole. It dug into the soil, and it found water ice, right there, just inches below the surface. The soil on Mars is called regolith. It's made of crushed rock, dust, and ice. The ice is water ice, H2O, the same stuff that makes up Earth's oceans. But it's frozen solid, because Mars is so cold, and because the pressure is so low. Here's the thing about water: it can exist in 3 states. Solid, like ice; liquid, like the water you drink; and gas, like steam. Which state it's in depends on 2 things: temperature and pressure. On Earth, at sea level, water freezes at 32 degrees Fahrenheit. It boils at 212 degrees Fahrenheit. Between those temperatures, it's liquid. You can drink it. On Mars, the pressure is so low that liquid water can't really exist on the surface. Even if you heated ice to above freezing, it would turn directly into gas. It would skip the liquid phase. This is called sublimation. The ice would turn into water vapor, into steam, and float away into the thin atmosphere. So you can't just dig up ice and let it melt. You need a different approach. You need chemistry. Here's what you do. You dig up the Martian soil, the regolith. You put it in a container. You seal the container. You heat it up. As the ice heats up, it turns into water vapor. The vapor rises. You capture it. You cool it down, and it turns back into liquid water. This process is called distillation. It's one of the oldest chemical techniques humans have used. People have been distilling liquids for thousands of years. To make alcohol, to purify water, to separate different substances. You're doing the same thing, but instead of distilling wine or seawater, you're distilling Martian soil. You're separating water from dirt, from rocks, from everything else. The basic setup is simple. You need a container to hold the soil. You need a way to heat it, maybe solar power, maybe a small heater. You need a tube or pipe to carry the vapor. And you need a cool place to condense it, to turn the vapor back into liquid. But the details matter: the temperature you heat to, the pressure you maintain, the rate of heating. All of these affect how much water you get, how efficiently you extract it. If you heat too quickly, you might lose water. It might escape before you can capture it. If you heat too slowly, you waste energy. You take too long. You need to find the right balance, the optimal temperature, the optimal rate. Scientists have studied this. They've tested different temperatures, different pressures, different methods. They've found that heating to about 350 degrees Fahrenheit works well. That's hot enough to release the water, but not so hot that you waste energy or create other problems. The pressure matters too. If you can increase the pressure in your container, you can extract water at lower temperatures. That saves energy, but increasing pressure requires equipment, pumps, seals, more complexity, more things that can break. So you need to balance simplicity with efficiency. Start simple. Get it working, then improve, optimize, make it better over time. That's how survival works, one step at a time, one improvement at a time. As the soil heats up, the ice sublimates, turns directly from solid to gas. The water vapor rises, it travels through your tube, it reaches the cool area. the temperature drops, the vapor condenses, turns back into liquid, drips into a collection container. You've just made water from Martian soil, using chemistry. But wait, is this water safe to drink? Probably not yet. Martian soil isn't just dirt and ice, it contains chemicals. Some of them are toxic. The most dangerous one is called perchlorate. Perchlorates are chemicals that contain chlorine and oxygen. They're used on Earth, in rocket fuel, in fireworks. They're not something you want in your drinking water. In 2008, when Phoenix dug into Martian soil, it found perchlorates. Scientists were surprised and worried. Because perchlorates are toxic to humans, they can damage your thyroid gland, they can interfere with how your body uses iodine. Long-term exposure can cause serious health problems. But here's something interesting. While perchlorates are toxic to humans, some Earth bacteria can actually eat them. Scientists have found bacteria in places like the Atacama Desert in Chile, a place so dry and harsh it's often used as a Mars analog. These bacteria break down perchlorates, use them as food, so maybe, in the future, we could use bacteria to clean Martian soil, to remove the toxins naturally. It's an idea scientists are exploring, using biology to solve chemistry problems. For now though, you'll need chemistry, you'll need to remove perchlorates yourself. Through heating, through washing, through chemical processes. It's work. But it's possible. So the water you extract from Martian soil will contain perchlorates and other chemicals. It won't be safe to drink, not yet. You need to purify it. You need to remove the toxins. And chemistry can help you do that too. There are several ways to purify water. Filtration is one. You can filter out solid particles. But perchlorates dissolve in water. They're too small to filter out easily. Distillation helps. When you distill water, you're separating it from other substances. But some chemicals can evaporate along with the water. Perchlorates might not, but you need to be careful. A better approach might be to wash the soil first, before you extract the water. You could rinse the soil with clean water, if you had any, or you could use a chemical process to break down the perchlorates. Actually, here's an interesting fact. Perchlorates break down when heated. At high temperatures they decompose, turn into safer chemicals. So if you heat your soil hot enough, you might destroy the perchlorates before you extract the water. But you need to be careful. Too much heat, and you might create other problems. You might release other toxic chemicals. You need to find the right temperature, the right process. Scientists are working on this right now. NASA is planning future Mars missions. They're designing systems to extract and purify water from Martian soil. They're testing different methods, different temperatures, different chemical processes. One method involves heating the soil to about 350 degrees Fahrenheit. This is hot enough to release the water, hot enough to break down perchlorates, but not so hot that it causes other problems. NASA is developing a system called the Water Extraction from Martian Regolith system. It's designed to extract water from soil, using heat, using pressure, using chemistry. The system heats the soil, captures the water vapor, condenses it, purifies it, all in one process. It's efficient. It's designed for future Mars missions, for astronauts, for survival. The system is being tested on Earth. Using simulated Martian soil, scientists are learning how much water they can extract, how much energy it takes, how to optimize the process. They're finding that you can extract about 2 to 5% water by weight from typical Martian soil. That means from 100 pounds of soil, you might get 2 to 5 pounds of water. That's about 1 to 2.5 liters. not much. But it's something. And if you process enough soil, you can get enough water to survive, to thrive. The system also needs to handle the perchlorates, remove them, or break them down. Scientists are testing different methods. Heating to high temperatures works, but takes energy. Chemical treatment works, but requires chemicals. You might need to combine methods. Use multiple steps to get truly clean water, safe water, water you can drink. Another method uses something called reverse osmosis. This forces water through a special membrane. The membrane blocks larger molecules, like perchlorates, lets pure water through. It's the same technology used to purify water on Earth, in desalination plants, on submarines, on the International Space Station. It works, it's proven. It could work on Mars too. But reverse osmosis requires pressure, high pressure, to force water through the membrane. That requires pumps, energy, equipment. So it's more complex than simple distillation. But it might be more efficient, more thorough, better at removing contaminants. You might need to combine methods. Use distillation first to extract water from soil. Then use reverse osmosis to purify it further. Remove any remaining contaminants. Create truly safe, clean water. It's a multi-step process. But it works, with science, with understanding, with the right equipment. You might not have fancy equipment, but you have chemistry. You understand how substances behave, how they react to heat, how they separate. You can experiment, you can test, you can find what works. Let's say you succeed. You've extracted water from Martian soil, you've purified it, you have clean, safe water. How much do you need? An average person needs about 2 to 3 liters of water per day. That's about half a gallon. More if you're active, more if it's hot, less if you're conserving. But let's say you need 2 liters per day. If you can extract water from Martian soil, you might be able to get about 2% water by weight. That means if you process 100 pounds of soil, you might get 2 pounds of water. That's about 1 liter. So to get your daily 2 liters, you'd need to process about 200 pounds of soil every single day. That's a lot of work, a lot of energy, a lot of time. But it's possible, with the right equipment, with the right process, with chemistry. But here's something interesting. You're not just making water for drinking. You need water for other things too, for growing plants, for making oxygen, for cleaning, for everything. So you need to think about water systems, not just water extraction. You'll need to store water, keep it from freezing, keep it from evaporating. You'll need to recycle it, use it multiple times. Every drop counts. On Mars, water is more precious than gold, more precious than anything. You can collect water from the air. Your breath contains water vapor. When you exhale, you're losing water. You can capture that, condense it, reclaim it. Your sweat contains water. Your urine contains water. Everything contains water. And you can reclaim it. Purify it. Use it again. This is called water recycling. It's what they do on the International Space Station. They recycle about 93% of their water. They capture moisture from the air. They recycle urine. They purify everything. And they drink it. It's safe, it's clean, it's necessary. The ISS has a sophisticated water recycling system. It's called the Water Recovery System. It has multiple stages. First, it collects water from the air, condenses humidity. Then it processes urine, removes contaminants, purifies it. Then it combines everything, filters it, treats it, tests it, makes sure it's safe. Then it's ready to drink, or use for other purposes. The system recycles about 93% of water on the station. That's impressive. It means astronauts need very little new water from Earth. They can stay in space longer. They can be more independent, more self-sufficient. The system uses several technologies: distillation, to separate water from other substances; filtration, to remove particles; chemical treatment, to kill bacteria, to remove contaminants; ion exchange, to remove dissolved salts; reverse osmosis, to remove even smaller contaminants. It's a complex system, but it works, it's proven, it's reliable. On Mars you'd need something similar. Maybe simpler, maybe more basic. But the principle is the same. Collect water, purify it, use it. Collect it again, purify it again, use it again. The cycle continues. And you survive. The system is complex. It has filters, chemical processes, distillation units, all working together to create a closed-loop system, where water is reused, over and over, where almost nothing is wasted. On Mars, you'll need something similar, maybe simpler, maybe more basic. But the principle is the same. Collect water, purify it, use it, collect it again, purify it again, use it again. The cycle continues, and you survive. You'll also need to think about water quality, not just removing toxins, but also adding minerals. Your body needs certain minerals: calcium, magnesium, sodium. These are in Earth's water, naturally. But Martian water might not have them, or might have the wrong ones. So you might need to add minerals, or filter them out, depending on what you have, what you need. Water chemistry is complex, but understanding it is crucial for survival, for health, for everything. You'll also need to store water, keep it from freezing, keep it from evaporating. On Mars, water wants to freeze or evaporate. It doesn't want to stay liquid. So you need to control temperature, control pressure, keep water in the right conditions. You could store water in insulated containers, keep it warm, above freezing. But that takes energy, takes heaters, takes power. Or you could store it underground, where temperatures are more stable, where it's protected. But that requires digging, requires construction, requires work. You could also store water as ice, freeze it, keep it frozen, then melt it when you need it. Ice doesn't evaporate, it doesn't leak. It's stable, it's safe. But melting it takes energy, takes time, takes planning. The best approach might be a combination. Store some water as liquid, for immediate use. Store some as ice, for long-term reserves. Have multiple storage systems, multiple backups. So if one fails, you have others. So if you lose some water, you don't lose everything. On Mars, you'll need to do the same. Create a closed-loop water system. Extract water from soil. Recycle water from your body. Recycle water from plants. Use it. Purify it. Use it again. The cycle continues, and you survive. But water is just one part of survival. You also need air, breathable air. And Mars's atmosphere is poison. So how do you create oxygen? How do you make air you can breathe? That's where chemistry gets even more interesting. Because creating air is more complex than creating water. It requires more energy, more equipment, more understanding of chemical reactions. But it's possible, and chemistry shows you how. Chapter 3: Creating Breathable Air, the Chemistry of Life. You have water, that's great, but you still can't breathe. Your spacesuit is providing oxygen, for now. But spacesuits have limited supplies. The oxygen tanks will run out, the filters will get clogged, the systems will fail. And when they do, you'll need another source of air. Breathing is more complex than you might think. It's not just about getting oxygen, it's about a whole process. A chemical process that happens in your body, every second, every breath. When you inhale, you take in air, mostly nitrogen, about 21% oxygen. A tiny bit of other gases. The oxygen enters your lungs. passes through thin membranes into your blood, where it binds to hemoglobin, a protein in red blood cells. That carries it throughout your body. In your cells, oxygen is used in a process called cellular respiration. It combines with glucose, a sugar, to produce energy. Carbon dioxide is produced as waste. It's carried back to your lungs, exhaled. The cycle continues. But this process requires oxygen, a constant supply. Your body can't store much oxygen, maybe a few minutes worth. So you need a continuous supply, fresh air, with enough oxygen, or you die. On Mars there's no fresh air. No oxygen to breathe. You have to create it. Using chemistry, using science, using everything you know. To turn poison gas into breathable air, to keep yourself alive. Mars's atmosphere is 95% carbon dioxide. You can't breathe that. Your body needs oxygen, about 21% oxygen, like Earth's air. Or at least enough oxygen to keep you alive. So you need to create oxygen from carbon dioxide, from the air around you, and chemistry can help you do exactly that. Let's start with the simplest method, electrolysis of water. You remember water, H2O, 2 hydrogen atoms, 1 oxygen atom. If you can split water apart, you get hydrogen and oxygen. The oxygen is what you need. The hydrogen, that's useful too, but we'll get to that. How do you split water? You use electricity. You run an electric current through water. The electricity breaks the chemical bonds. The hydrogen and oxygen separate. Hydrogen gas bubbles up from one electrode. Oxygen gas bubbles up from the other. This process is called electrolysis. It's been known for over 200 years. Scientists have been doing it since the 1800s. In 1800, 2 English scientists, William Nicholson and Anthony Carlisle, discovered that running electricity through water could split it. They were amazed. They had found a way to create gases from water using electricity. Since then, electrolysis has been used for many things. To produce hydrogen for fuel. To produce oxygen for breathing. To produce chlorine for cleaning. It's a fundamental chemical process. And it's how the International Space Station creates oxygen for astronauts. The ISS has been continuously occupied since 2000. That's over 20 years. And for most of that time, it's been producing its own oxygen. Using electrolysis. Splitting water, creating oxygen. It works, it's reliable, it's proven technology. The ISS has a system called the Oxygen Generation System. It takes water from Earth, or water recycled from the station. It runs electricity through it. It splits the water. It collects the oxygen, pumps it into the station's air, the hydrogen. That gets vented into space, or used for other purposes. You could do the same thing. You have water now, from Martian soil. You have solar panels. They produce electricity. You connect them. You run current through the water. You collect the oxygen. You store it. You breathe it. But here's the thing. Pure water doesn't conduct electricity very well. You need to add something to it. An electrolyte. A substance that dissolves in water and allows electricity to flow. Salt works. Sodium chloride. When you add salt to water, it breaks apart into ions. Charged particles. These ions carry the electric current. So you add salt to your water, you run electricity through it, you get oxygen, and hydrogen, and salt water left behind. How much oxygen can you make? Let's do some math. 1 molecule of water, H2O, contains 1 oxygen atom. When you split it, you get half a molecule of oxygen gas, O2, because oxygen gas is made of 2 oxygen atoms bonded together. 1 liter of water weighs 1 kilogram. That's 1,000 grams. Water is mostly oxygen by weight, about 89%. So 1 liter of water contains about 890 grams of oxygen. When you split it, you get oxygen gas. About 622 liters of oxygen gas. At normal pressure, an average person breathes about 500 liters of oxygen per day, so 1 liter of water could provide more than a day's worth of oxygen. That's pretty good. But you need electricity, a lot of it. Electrolysis takes energy. You need solar panels, or batteries, or some other power source, and power is limited. But if you can generate enough electricity, you can make oxygen from water using chemistry. But wait, there's another way, a way that uses carbon dioxide directly. The stuff that's already in Mars's atmosphere. Remember the Sabatier reaction? This is a chemical process that turns carbon dioxide and hydrogen into water and methane. It's named after a French chemist, Paul Sabatier, who discovered it in the early 1900s. Here's how it works. You take carbon dioxide, CO2. You take hydrogen, H2. You mix them together. You heat them up. You add a catalyst, a substance that speeds up the reaction, usually nickel or ruthenium metal. And the molecules rearrange. The carbon dioxide and hydrogen combine. They form water, H2O, and methane, CH4. This is useful for 2 reasons. First, you get water, more water, which you can use for drinking, or for making more oxygen through electrolysis. Second, you get methane. Methane is natural gas. You can burn it for fuel, for heat, for power, or, if you're really ambitious, for rocket fuel to get home. The Sabatier reaction is actually planned for future Mars missions. NASA is developing systems that will use it to create fuel for return trips, to create water, to create oxygen, all from carbon dioxide in the atmosphere. And hydrogen from water. It's a closed loop. Everything gets reused, recycled, nothing wasted. The reaction needs a catalyst, usually nickel or ruthenium. These metals speed up the reaction, make it happen faster, at lower temperatures. Without a catalyst, you'd need much higher temperatures, much more energy. The catalyst makes it practical, makes it possible. The reaction also produces heat as a byproduct, so you can use that heat for other purposes, for warming your habitat, for heating water, for powering other systems. It's efficient, it's smart, it's using everything, wasting nothing. But the Sabatier reaction has a problem. It needs hydrogen, and hydrogen is hard to get. You can get it from water, through electrolysis. But that takes energy, takes water. So you're trading one resource for another. It's a balance, a trade-off. You need to decide what's most important. What you need most: water, oxygen, fuel. The answer depends on your situation, on your priorities, on your survival needs. But here's the really cool part. You can also reverse this process. Sort of. You can use electricity to turn carbon dioxide directly into oxygen and carbon monoxide. This is called electrolysis of carbon dioxide, or CO2 electrolysis. NASA is actually testing this right now. On Mars, the Perseverance rover, which landed in 2021, has an experiment called MOXIE. That stands for Mars Oxygen ISRU experiment. ISRU means in situ resource utilization, using resources that are already there. MOXIE takes carbon dioxide from Mars's atmosphere. It compresses it, it heats it up to about 1,400 degrees Fahrenheit. It runs electricity through it. and it splits the carbon dioxide it produces oxygen and carbon monoxide. In its first test, MOXIE produced about 5.4 grams of oxygen. That's enough for about 10 minutes of breathing, not much, but it proved the concept works on Mars, using real Martian air. Over time, MOXIE has produced more oxygen. In one test, it produced about 10.5 grams. That's enough for about 20 minutes of breathing. Still not much. But it's improving. NASA is learning. Improving the process. Testing different conditions, different temperatures, different pressures. MOXIE has run multiple times. Dozens of times. Each time, it produces oxygen. Consistently, reliably, it proves the concept works. On Mars. Using real Martian air. In real conditions. The process MOXIE uses is called solid oxide electrolysis. It's a type of high-temperature electrolysis. The carbon dioxide is compressed. Heated to about 1,400 degrees Fahrenheit. That's hot. Hotter than molten lava. At that temperature, the carbon dioxide molecules become more reactive. More willing to break apart. The solid oxide part refers to the electrolyte, a ceramic material, usually made of zirconia, doped with other elements, like yttria. This material conducts oxygen ions, but not electrons. So when you apply electricity, oxygen ions move through it, from one side to the other. This separates the oxygen from the carbon, creates pure oxygen gas. The process is efficient, about 70% efficient. That means for every unit of energy you put in, you get 0.7 units of oxygen out. Not perfect, but good. Better than many other methods. And it works. On Mars. In real conditions. With real Martian air. MOXIE has run dozens of times. Produced oxygen consistently. Proved the concept works. Now NASA is planning bigger versions. Versions that could produce enough oxygen for astronauts. For a whole mission. For survival. Then electricity is applied. The electric current helps break the chemical bonds. The carbon dioxide splits into carbon monoxide and oxygen. The oxygen is collected, purified, stored, ready to breathe. The carbon monoxide, that's a problem, it's toxic. But MOXIE releases it back into the atmosphere. On Mars that's fine, there's no one to harm. But in a habitat you'd need to handle it differently. Maybe convert it to something safer. Or use it for something else. Carbon monoxide can be used in chemical reactions to make other compounds. So it's not completely useless, just dangerous if you breathe it. Scientists are working on improving the process, making it more efficient, producing more oxygen, using less energy, because energy is precious on Mars. Every watt counts. And NASA is planning bigger versions. A version 100 times larger than MOXIE, that could produce enough oxygen for 4 astronauts. For a whole mission. For months, maybe years. It's called MOXIE 2.0. Or maybe it'll have a different name. But the concept is the same. Bigger, better, more efficient. The technology is real, it's working, right now, on Mars. And you could use the same principles, the same science, to create your own oxygen, to breathe, to survive. You probably don't have MOXIE, but you understand the science. You know that carbon dioxide can be split. You know that electricity can break chemical bonds. You know that chemistry can turn poison gas into breathable air. So you have options. You can make oxygen from water. Through electrolysis. You can make oxygen from carbon dioxide. Through high-temperature electrolysis. You can make water from carbon dioxide and hydrogen. through the Sabatier reaction, and then make oxygen from that water. All of these methods use chemistry. They all require energy, they all require equipment. But they're all possible, with the right knowledge, with the right materials, with science. But creating oxygen is just part of the challenge. You also need to manage the air you breathe. On Earth, air is about 78% nitrogen, 21% oxygen, and 1% other gases. That mix is important. Pure oxygen can be dangerous. It's flammable. It can damage your lungs if the pressure is too high. So you might want to mix your oxygen with nitrogen, or with other gases, to create a breathable atmosphere, like Earth's air. But where do you get nitrogen? Mars's atmosphere has some nitrogen, about 2.7%. You could extract it, separate it from the carbon dioxide, use it to dilute your oxygen. Create a safer breathing mix. You'll also need to remove carbon dioxide from your air. When you breathe, you exhale carbon dioxide. It builds up. Too much carbon dioxide is toxic. It can cause headaches, dizziness, confusion, eventually death. So you need to scrub it out, remove it, keep the air clean. On the International Space Station, they use something called a carbon dioxide removal assembly. It uses chemicals called amines. These chemicals absorb carbon dioxide. Then they're heated. The carbon dioxide is released, vented into space. The chemicals are reused. The cycle continues. The system is called CDRA. Carbon dioxide removal assembly. It has two beds. One absorbs carbon dioxide, while the other releases it. They alternate, so there's always one working. Always removing carbon dioxide, keeping the air clean. But venting carbon dioxide into space wastes it. On Mars you might want to keep it, use it, turn it into oxygen through MOXIE-like processes, or use it for plants. Plants need carbon dioxide, they breathe it in, use it for photosynthesis, so you could route carbon dioxide to your greenhouse. Let plants clean the air, while also producing food. It's efficient, it's smart, it's using everything, wasting nothing. You'll also need to monitor air quality, oxygen levels, carbon dioxide levels, other gases, humidity, pressure, temperature. Everything matters. Too much oxygen, and things become flammable. Too little, and you suffocate. Too much carbon dioxide, and you get headaches, dizziness, confusion. You need to keep everything balanced, in the right ranges. For health, for safety, for survival. You'll need sensors, monitors, alarms, to track air quality, to warn you if something's wrong, if oxygen drops too low, if carbon dioxide builds up, if pressure changes. So you can fix problems before they become dangerous, so you can maintain a safe environment, so you can survive. You'll also need to think about pressure. Not just composition, but pressure itself. Your habitat needs to maintain pressure, Earth-like pressure, so you can breathe comfortably, so your body works normally, so you don't have problems with your ears, your sinuses, your lungs. Maintaining pressure means your habitat needs to be sealed, airtight, no leaks. Because if air leaks out, pressure drops, and you'll need to replace it, which takes energy, takes resources. So you need to fix leaks, maintain seals, keep everything tight, keep everything working. Pressure also affects how gases behave. At higher pressure, gases dissolve better in liquids. At lower pressure, they escape. So pressure affects your water systems, your plant systems, everything. You need to understand how pressure works, how it affects things. how to control it, how to use it. Air management is a constant task, a constant challenge. But with chemistry, with understanding, with systems, you can do it, you can breathe, you can survive. You could do something similar, use chemicals to absorb carbon dioxide, or use plants. Plants take in carbon dioxide, they use it for photosynthesis, they release oxygen. So plants can help clean your air, while also providing food. It's a win-win. Creating and managing air is complex. It requires chemistry, physics, biology, all working together, but it's possible, and with science you can do it. Let's say you succeed. You have water, you have oxygen, you can breathe, you can drink. You can survive for weeks, maybe months, but you still need food. Because emergency rations will run out. And you can't survive on water and air alone. You need nutrients. You need energy. You need to grow food. And that's where biology meets chemistry, on Mars. Because growing food isn't just about plants, it's about creating an ecosystem. A closed system, where everything works together, where waste becomes food, where life sustains life. Chapter 4. Growing Food. Biology meets chemistry. Food is energy. Your body needs calories. It needs nutrients, vitamins, minerals, protein, carbohydrates, fats. Without food, you'll starve. Your body will start eating itself, breaking down muscle, organs. You'll weaken, you'll die. In about 3 weeks without food. Maybe a month if you have water. Your emergency rations won't last forever. Maybe you have a few weeks worth, maybe a month. But then what? You need to grow food. On Mars. In soil that wants to kill plants. Martian soil is not friendly. It's not like Earth soil. Earth soil is alive. It's full of organic matter, dead plants, dead animals, microbes, worms, all working together, creating nutrients, creating structure, creating life. Martian soil is dead. It's sterile. It's just crushed rock, dust, ice, and chemicals, toxic chemicals. Remember perchlorates? Those toxic chemicals we found in the water, they're also in the soil, and they're not the only problem. Martian soil is also very alkaline. The pH is high, around 8 or 9. Most plants like neutral soil. pH around 7. Or slightly acidic, around 6. Martian soil also lacks nitrogen. Plants need nitrogen. It's essential for growth, for making proteins, for making chlorophyll. The green stuff that lets plants use sunlight. Martian soil lacks organic matter, dead plant material, compost, the stuff that feeds soil, that holds water, that provides nutrients. So Martian soil has everything plants don't want, and nothing plants do want. It's like trying to grow a garden in concrete, with poison mixed in. But scientists have been experimenting. They've been testing. Can plants grow in Martian soil? The answer is, maybe, with help. In 2014, scientists at Wageningen University in the Netherlands did an experiment. They got simulated Martian soil from NASA. Soil that matches what we know about Mars. They tried to grow plants in it, tomatoes, ryegrass, peas, radishes. The plants grew, but not well. They were small, weak. They produced less food than plants grown in Earth soil, but they grew, they survived, they produced food. The scientists continued their experiments. In 2016, they grew 10 different crops, including tomatoes, peas, rye, radish, rocket, cress, quinoa, spinach, chives, and leeks. They added organic matter. They added nutrients. They watered the plants. And most of them grew. They even produced seeds, which could be used to grow more plants. In 2019, they tried growing in simulated moon soil too, and they found something interesting. Plants grew better in Martian soil than in Moon soil. Martian soil has more nutrients, more minerals. It's more like Earth soil, just with toxins that need to be removed. Other scientists have done similar experiments. At NASA's Kennedy Space Center, at universities around the world, they're all learning, improving techniques, finding what works, what doesn't. At the University of Florida, scientists grew Arabidopsis plants, a small flowering plant often used in research. They grew it in simulated Martian soil, with some Earth soil mixed in, just 10% Earth soil, 90% Martian soil. And the plants grew, not as well as in pure Earth soil, but they grew, they flowered, they produced seeds. The key was the Earth soil. It provided microbes, beneficial bacteria, fungi, tiny organisms that help plants, that break down nutrients, that create a healthy soil ecosystem. So maybe the solution isn't just cleaning Martian soil. Maybe it's adding life to it, bringing Earth's soil ecosystem to Mars, one small batch at a time. At the International Space Station, astronauts have grown lettuce, radishes, even chili peppers, in space, in zero gravity, using hydroponics, LED lights, controlled conditions. And it works. The food is safe to eat, it's nutritious, it's fresh. It's proof that growing food in space is possible. That it can work on Mars too. The veggie system on the ISS uses special plant pillows, bags filled with a growth medium, like clay pellets, or special soil. Seeds are planted in them, watered, given nutrients, lit with LED lights, red and blue LEDs, the colors plants use most. The system is simple, but effective. Astronauts have harvested lettuce, eaten it, enjoyed it, fresh food in space, something that was impossible just a few years ago. The system also helps with air quality. Plants take in carbon dioxide, release oxygen, they help clean the air, they help create a better environment. They're not just food, they're part of the life support system, part of survival. On Mars you'd use similar systems, maybe adapted for Martian conditions, for lower gravity, for different pressures, but the principles are the same. Plants need light, water, nutrients, carbon dioxide. Give them those, and they grow, they produce food, they help you survive. The results are promising. Growing food on Mars is possible. Difficult, but possible. It requires science. It requires understanding. It requires patience. But it can be done. The key was adding things. The scientists added organic matter, compost. They added nutrients. They watered the plants. They gave them light, and the plants grew. So it's possible. But you need to prepare the soil, you need to wash it, remove toxins, add nutrients, add organic matter, create the right conditions. Let's start with washing. You need to remove perchlorates and other toxins. You can do this by rinsing the soil with water, lots of water. The perchlorates dissolve. They wash away, you're left with cleaner soil, still not perfect, but better. But wait, you don't have lots of water. Water is precious, you can't waste it washing soil. So you need to be smart. You need to recycle. You can collect the wash water, filter it, remove the toxins, reuse it, or you can use a different method. Actually, remember how perchlorates break down when heated? You could heat the soil, destroy the perchlorates, then use the soil, but heating takes energy. And you need to be careful not to destroy other things the plants might need. Let's say you've cleaned the soil, as much as you can. Now you need to add nutrients. Plants need 3 main nutrients: nitrogen, phosphorus, and potassium. They need other things too: calcium, magnesium, sulfur, trace elements, iron, zinc, copper, Where do you get these? From your waste. Seriously. Your urine contains nitrogen, phosphorus, potassium, all the things plants need. You can dilute it, add it to water, use it to fertilize your plants. This is called using human waste as fertilizer. It's been done on Earth for thousands of years. Farmers have used manure, compost, human waste to feed crops. It works. It's natural. It's a closed loop. You eat food, you produce waste. The waste feeds plants, the plants feed you, the cycle continues. You'll also need to adjust the pH. Make the soil less alkaline, more neutral. You can do this by adding acid, or by adding organic matter, compost, dead plant material. As it breaks down, it releases acids, lowers the pH. But where do you get organic matter? At first you don't have any. You'll need to create it. You can use parts of plants you don't eat, stems, leaves, roots. You can compost them, let them break down, create soil. Over time your soil will get better, richer, more alive. You'll also need to add structure. Martian soil is fine, dusty. It doesn't hold water well. It doesn't have air pockets. Plant roots need air. They need space to grow. You can add things to create structure, sand, gravel, or better yet, you could use a different approach entirely. Hydroponics. Instead of growing plants in soil, you grow them in water. You provide all the nutrients directly. In the water, the plants' roots hang in the nutrient solution. They get everything they need. No soil needed. Hydroponics has advantages. You use less water. The water is recycled. You have more control. You can grow plants faster, in less space. Many space missions plan to use hydroponics. The International Space Station grows plants hydroponically. But hydroponics requires equipment, pumps, tubes, reservoirs, nutrient solutions. It's more complex, more things that can break. Maybe you start with soil. Simple, basic. You prepare it as best you can. You plant seeds. You water them. You give them light, and you see what happens. But where do you get light? Mars gets sunlight, but less than Earth. About 43% as much. And you're probably growing plants inside, in a habitat, for protection. So you need artificial light. LED lights work well. They're efficient. They don't produce much heat. They can provide the right wavelengths, the colors plants need. Plants mostly use red and blue light. They reflect green light. That's why they look green. So you can use red and blue LEDs, save energy, give plants what they need. You also need to control temperature. Plants like it warm, around 70 degrees Fahrenheit. Mars is cold, especially at night. So you need heaters. Or you need to use the heat from your lights, from your other equipment. You need insulation to keep the warmth in, the cold out. And you need to control the atmosphere. Plants need carbon dioxide. They breathe it in, they use it to make food. Through photosynthesis. They take in CO2, they take in water, they use sunlight. And they make glucose, sugar, food. They release oxygen as a byproduct. So plants actually help you. They take the carbon dioxide you can't breathe, they turn it into oxygen you can breathe. They take the water you give them, they turn some of it into food you can eat. It's a partnership. You help them, they help you. But it takes time. Plants don't grow overnight. A lettuce plant might take 30 to 40 days. Tomatoes take 60 to 80 days. Potatoes take 90 to 120 days. You need patience. You need to plan ahead. You need to start growing food before you run out of rations. And you need variety. You can't survive on just one type of food. You need different nutrients, different vitamins. So you need to grow different plants. Leafy greens for vitamins, root vegetables for calories, legumes for protein, herbs for flavor and nutrition. It's a lot of work, a lot of systems, a lot of things that need to work together, but it's possible. With biology, with chemistry, with understanding how plants work, how ecosystems work, how life sustains itself. But growing food isn't just about plants. You also need to think about what you're growing. Some plants are better than others for survival. You want plants that grow fast, that produce a lot of food, that are nutritious, that are easy to grow. Leafy greens are good: lettuce, spinach, kale. They grow quickly, 30 to 40 days. They're full of vitamins. They don't need much space, but they don't provide many calories. You can't survive on lettuce alone. Root vegetables are better for calories. Potatoes, sweet potatoes, carrots. They take longer to grow, 60 to 90 days, but they store energy, carbohydrates. They can keep you alive, and they store well. You can harvest them, keep them for months. Legumes are important too. Beans, peas, lentils. They're high in protein, they're nutritious, and they help the soil. They have bacteria in their roots. These bacteria take nitrogen from the air, convert it into a form plants can use. They fertilize the soil naturally. You'll want a mix. Different plants, different nutrients, different harvest times. So you always have something growing, something ready to eat, something providing food. You'll also need to think about seeds. Where do you get them? Maybe you brought some from Earth, emergency seeds. Maybe you can save seeds from what you grow. Create your own seed bank. But you need variety, genetic diversity, so your crops don't all fail if one disease hits. Seeds are amazing. They're like tiny time capsules. They contain everything a plant needs to grow, encoded in DNA. They can survive for years, decades even, if stored properly. Cool, dry, protected from light, from moisture, from pests. On Mars, you'll need to store seeds carefully, protect them, keep them viable, so you can plant them, grow more food, create a sustainable system, where you're not just consuming, you're producing, creating, building. You'll also need to think about pollination. Many plants need pollinators, bees, butterflies, other insects. But on Mars there are no insects, so you'll need to pollinate by hand, or grow plants that don't need pollinators, or use other methods. Some plants are self-pollinating. They can pollinate themselves. Tomatoes, peas, beans. These are good choices. They're easier to grow. They don't need help. They just need the right conditions, and they'll produce food and seeds for the next generation. Other plants need help. You can pollinate them yourself, using a small brush or your finger, transferring pollen from one flower to another. It's tedious, but it works, and it's necessary if you want to grow those plants, if you want variety in your diet. And you need to think about pests. On Earth, insects eat crops. On Mars, there are no insects. But there might be other problems: mold, bacteria, diseases. You need to keep things clean, sterile, controlled. Growing food on Mars is like running a laboratory. Everything is controlled. Everything is monitored. Everything is optimized. It's not farming like on Earth. It's more like science. Precise, careful, systematic. But you're not just growing plants. You're creating an ecosystem. A closed system, where everything works together. Plants produce oxygen. You breathe it. You produce carbon dioxide. Plants use it. Plants produce food. You eat it. You produce waste. Plants use it. The cycle continues. This is called a closed-loop system, or a bioregenerative life support system. It's what scientists are planning for Mars colonies, for long-term space missions, where you can't resupply, where you need to be self-sufficient, where everything needs to work together. The key is balance. You need enough plants to produce enough oxygen, but not so many that they consume too much carbon dioxide. You need enough plants to produce enough food, but not so many that they need too much water, too much light, too much space. Scientists have calculated that you'd need about 20 square meters of growing area per person to produce enough oxygen, enough food. That's about 200 square feet, the size of a small room. But you'd need to optimize it, use vertical growing, stack plants, use every inch of space, make it efficient, make it productive. You'd also need to think about what to grow. Some plants are better than others. Fast-growing plants like lettuce and radishes are good. They produce food quickly, but they don't provide many calories. Slow-growing plants like potatoes and sweet potatoes are better for calories, but they take longer. You need a mix. Fast growers for immediate food, slow growers for long-term sustenance. You'd also need to think about nutrition. Different plants provide different nutrients. Leafy greens provide vitamins. Root vegetables provide carbohydrates. Legumes provide protein. You need variety to get all the nutrients your body needs, to stay healthy, to survive. And you need to think about seeds, saving seeds, creating a seed bank, so you can keep growing, year after year, generation after generation. So your food system is sustainable, so it can last, so you can survive long term. You need to think about the whole system, not just individual parts. How does water flow? How does air circulate? How does energy move? How do nutrients cycle? Everything is connected, everything affects everything else. It's complex, it's challenging, but it's possible, and it's necessary for long-term survival, for building a future on Mars, using science, using understanding, using everything you know. But all of this requires power. Lights need electricity, pumps need electricity, heaters need electricity, everything needs power, and power is limited. So how do you generate enough? How do you keep everything running? That's where physics comes in, because power is all about energy, and physics is the science of energy. How it moves, how it transforms, how you can capture it, use it, store it. Chapter 5. Generating power. Physics keeps everything running. Everything needs power. Your spacesuit needs power to keep you warm, to circulate air, to run its computers. Your water extraction system needs power to heat the soil, to run pumps. Your oxygen generator needs power to run electrolysis, to compress gases. Your greenhouse needs power for lights, for pumps, for heaters. Without power, everything stops. Your spacesuit fails. You freeze, you suffocate. Your water system stops. You dehydrate, your oxygen system stops. You can't breathe. Your greenhouse stops. Your plants die. You starve. Power is life on Mars more than anywhere else. So where do you get power? You have a few options. Let's start with the most obvious one: solar power. Mars gets sunlight, less than Earth, but still plenty. About 43% as much solar energy as Earth. That's enough. Solar panels can work on Mars. They do work on Mars. Many Mars rovers use solar panels. Spirit and Opportunity. The InSight lander. The Ingenuity helicopter. Solar panels work by converting sunlight into electricity. They're made of special materials called semiconductors, usually silicon. When sunlight hits these materials, it knocks electrons loose, creates an electric current. This is called the photovoltaic effect. Photo means light, voltaic means electricity. The photovoltaic effect was discovered in 1839 by a French physicist named Alexandre Edmond Becquerel. He was only 19 years old. He found that certain materials produce electricity when exposed to light. But it took over 100 years before we could make practical solar cells. The first modern solar cell was made in 1954 at Bell Labs. It was only about 6% efficient. Today's solar cells can be over 20% efficient. Some experimental ones are even higher. On Mars, solar panels work, but they're less efficient than on Earth. Because Mars gets less sunlight, about 43% as much, so you need more panels. Or more efficient panels. Or both. But there's another problem: dust. Martian dust is fine, powdery, it gets everywhere, and it accumulates on solar panels. Blocks sunlight, reduces efficiency. The Opportunity rover lost power during a dust storm. But even on clear days, dust builds up. Slowly. Steadily. Reducing power output over time. So you'll need to clean your panels. Regularly, maybe daily, maybe weekly, depending on conditions. You could use brushes. Or compressed air. Or even just tilt the panels, let the wind blow dust off. But wind on Mars is weak, so manual cleaning might be necessary. Some missions have tried self-cleaning panels, using vibration, or special coatings, that repel dust. These technologies are improving. But for now, you'll probably need to clean panels yourself. It's work. But it's necessary. Despite these challenges, solar power is still your best option. For now. It's reliable. During the day, it's proven. Many Mars missions use it. And it's something you can maintain. Fix. Improve. With the right knowledge. With the right tools. With science. You probably have solar panels. On your ship. Or you can salvage them. Set them up, point them at the sun. They'll generate electricity. During the day. But Mars has a problem. Dust storms. Massive dust storms. They can cover the entire planet. They can last for weeks. Or months. During a dust storm, the sky turns dark. Sunlight can't reach the surface. Your solar panels stop working. No power. This happened to the Opportunity rover. In 2018, a global dust storm covered Mars. Opportunity's solar panels couldn't get enough sunlight. The rover's batteries ran out. It went silent. NASA tried to contact it for months. But it never responded. The mission was declared over. So solar power works. But it's unreliable. You need backup, you need storage, you need batteries to store power for the night. For dust storms. For emergencies. Batteries store chemical energy. When you charge them, electricity flows in. It causes chemical reactions, stores energy. When you use them, the reactions reverse, release energy, as electricity. But batteries have limits. They can only store so much energy. They degrade over time. They lose capacity, they can fail. And on Mars, you probably don't have unlimited batteries. There are different types of batteries. Lithium-ion batteries are common. They're used in phones, laptops, electric cars. They're efficient, they hold a lot of energy. But they degrade. After a few years, they lose capacity. They don't hold as much charge. And they can be dangerous if damaged. They can catch fire, explode even. Lead-acid batteries are older technology. But they're reliable. They last longer. They're easier to maintain. But they're heavier. Less efficient. They take up more space. For the same amount of energy. You'll need to manage your batteries carefully, not overcharge them, not drain them completely, keep them at the right temperature. Too cold and they lose capacity. Too hot, and they degrade faster. You need to find the sweet spot, the optimal conditions. You'll also need to think about battery life. How long will they last? A few years, maybe, but eventually, they'll fail, and you'll need replacements. Or you'll need to find another way to store energy. or generate it continuously. So you don't need as much storage. That's why nuclear power is attractive. RTGs produce power continuously, day and night, through dust storms, through everything. They don't need batteries, they don't need storage, they just work, for decades. But they're expensive, dangerous, highly regulated. You probably don't have one. So you need other options. What else can you use? Nuclear power. This is what the Curiosity and Perseverance rovers use. They have something called a radioisotope thermoelectric generator, an RTG. An RTG uses radioactive material, usually plutonium-238. As this material decays, it produces heat. A lot of heat. The RTG uses something called a thermocouple to convert that heat into electricity. It's basically a nuclear battery. It produces power continuously. For years, decades even. The Curiosity rover's RTG produces about 110 watts of power. That's not much, about as much as a bright light bulb, but it's constant. Day and night. Through dust storms. Through everything. You probably don't have an RTG. They're expensive, dangerous, highly regulated, but understanding how they work helps. It shows that nuclear power is possible, even on Mars. What about wind power? Mars has wind, strong wind sometimes. During dust storms, winds can reach 60 miles per hour. Or more. But Mars's atmosphere is thin. Really thin. So even strong winds don't have much force. They don't have much energy. Wind power works by using the wind to turn a turbine. The turbine spins a generator, creates electricity. But the amount of power depends on the density of the air. And Mars's air is about 1% as dense as Earth's. So even a 60-mile-per-hour wind on Mars has about 1% of the energy of a 60-mile-per-hour wind on Earth. That's not much. Wind power on Mars is possible. But not very efficient, not very reliable. What about other options? Geothermal power, using heat from inside the planet. Mars is geologically dead, mostly. There's not much heat coming from inside, not like Earth, so geothermal isn't really an option. But there might be other ways to generate power. What about using temperature differences? Mars has huge temperature swings, day and night. You could use that. A device called a thermoelectric generator converts heat differences into electricity. You could use the temperature difference between day and night, between inside and outside, between different parts of your habitat. It wouldn't produce much power, but every bit helps. What about using chemical reactions? Some chemical reactions produce electricity directly, like batteries. But instead of storing energy, they generate it. Fuel cells do this. They combine hydrogen and oxygen, produce electricity, and water. You have both. Hydrogen from electrolysis, oxygen from air production. You could use them, generate power, and get water back. It's efficient. It's useful. What about using mechanical energy? Wind might not be strong enough for turbines. But what about using your own movement? Piezoelectric materials generate electricity when pressed. When flexed, you could put them in floors, in equipment. Every step, every movement generates a tiny bit of power. Not much, but it adds up over time. The key is to use everything, every source of energy, every opportunity. Solar power is your main source. But backups help. Alternatives help. Diversity helps. So if one thing fails, you have others. You're not dependent on just one thing. You're resilient. You're prepared. What about chemical power? Fuel cells. These combine hydrogen and oxygen to produce electricity, and water as a byproduct. You have hydrogen from electrolyzing water. You have oxygen From making air, you could combine them, generate power, and get water back. Fuel cells are efficient, they're used in spacecraft, they're reliable. But they consume fuel, hydrogen and oxygen, and you need those for other things. For making water, for breathing, so it's a trade-off. Maybe the best approach is a combination. Use solar power as your main source. During the day, store excess in batteries. Use those batteries at night, during dust storms. Have backup systems, fuel cells, maybe even a small nuclear generator if you have one, and conserve. Use power efficiently. Turn off lights you don't need. Insulate everything. Keep heat in. Reduce waste. Every watt counts. You also need to think about the long term. Solar panels degrade. They lose efficiency over time. Batteries degrade. They lose capacity. Systems break. They need maintenance. You're alone, you need to fix everything yourself, with limited tools, limited parts. But power isn't just about generation. It's also about efficiency, using less power, making everything more efficient. Every light bulb, every heater, every pump, every system. LED lights are efficient. They use less power than old light bulbs. They last longer. They don't produce much heat. Which is good. Because heat is wasted energy. On Mars you can't afford to waste anything. Insulation is important too. Good insulation keeps heat in, reduces the need for heaters, saves power. You can use Martian soil, regolith. It's a good insulator. You can pile it up, cover your habitat, create a barrier, keep the cold out, keep the heat in. You can also use passive systems, systems that don't need power. Like using sunlight directly, through windows, for light, for heat. Like using thermal mass, materials that store heat, release it slowly. Like rocks, water. They absorb heat during the day, release it at night, without using any power. Every little bit helps. Every watt saved is a watt you don't need to generate. Every efficiency improvement extends your survival, makes everything easier, more sustainable. You can also use smart systems, systems that only use power when needed. Motion sensors for lights, timers for heaters, automatic shutoffs, so things turn off when you're not using them, so power isn't wasted, so energy is conserved. You can also prioritize, use power for the most important things first, life support, water, air, food, then for comfort, then for everything else. So if power is limited, the essentials still work, so you still survive, even if other things have to wait. You can also schedule. Do energy-intensive tasks during the day. When solar power is available, save battery power for the night, for emergencies, for when you really need it. So you're using power efficiently, so you're making the most of what you have. Energy management is crucial. It's not just about generating power. It's about using it wisely, about conserving it, about making it last. Because power is life, and every watt counts. But power is still a challenge. Solar power is unreliable. Batteries degrade. Systems break. You need backups, redundancy, multiple ways to generate power, multiple ways to store it, multiple ways to use it. You might have a small nuclear generator, if you're lucky, or you might need to rely on solar, with lots of batteries, with careful management, with conservation. It's possible, but it's hard, really hard. Power's life, on Mars, more than anywhere. Without it, everything stops, but with physics, with understanding energy, with creativity, you can keep the lights on, you can keep everything running, at least for a while. But surviving day 1 is one thing. Surviving day 100? Day 1000? That's different. That requires systems, planning, thinking ahead. And maybe most importantly, it requires mental strength. Because the physical challenges are hard, but the mental challenges might be harder. Chapter 6. The Long-Term Challenge. Building a Future. You've survived the first day, the first week, maybe the first month. You have water, you have air. You have food growing. You have power. Things are working. For now. But here's the reality. Everything is connected. Your water system feeds your oxygen system. Your oxygen system keeps you alive. Your power system runs everything. Your food system feeds you. If one thing fails, it can cascade, cause other failures. And then everything fails. This is called systems thinking. Understanding how everything connects, how everything depends on everything else. It's like a web. Pull one thread, and the whole thing can unravel. Systems thinking is crucial for survival. You need to understand not just individual parts, but how they work together, how they affect each other, how changes in one part ripple through the whole system. For example, if your power system fails, it doesn't just mean no lights. It means no heaters, no water pumps, no air circulation, no oxygen production, no food growth. Everything stops. Because everything depends on power. But if you understand the system, you can prepare, you can build redundancy, you can create backups, you can design fail-safes, systems that kick in when others fail, that keep things running, that prevent cascading failures. You also need to think about maintenance. Everything breaks, everything wears out. You need spare parts, tools, knowledge. You need to be able to fix things, repair them, improve them. Because you can't just call for help. You're on your own. You're the engineer, the mechanic, the technician, everything. And you need to think about the long term, not just surviving today, but surviving tomorrow, next week, next month, next year. You need to plan ahead, stockpile resources, build reserves, create buffers. So when things go wrong, you have time to fix them. You have resources to use. You have options. Systems thinking is about seeing the big picture, understanding connections, planning for the future, building resilience. It's about being smart, being prepared, being ready for anything. Let's say your power system fails. Your solar panels get covered in dust. Your batteries die. No power. Your heaters stop. You freeze. Your water system stops. You dehydrate. Your oxygen system stops. You suffocate. Your greenhouse lights go out. Your plants die. You starve. One failure, multiple consequences. That's why you need redundancy. Backup systems. Multiple ways to do everything. If one thing breaks, you have another. If that breaks, you have another. As many backups as possible. You also need to maintain everything. Clean solar panels, replace filters, fix leaks, repair equipment. Everything breaks. Everything wears out. You need to be ready. You need spare parts. You need tools. You need knowledge. But maybe the biggest challenge isn't physical, it's mental. You're alone. Completely alone. No other humans, no one to talk to, no one to help, no one to share the burden. Just you, and Mars. And silence. Humans are social creatures. We evolved in groups. We need connection. We need community. Isolation is hard. Really hard. It can break you. Mentally. Emotionally. Scientists have studied this. They've run experiments, simulating Mars missions on Earth, in places like Hawaii, in the High Seas Project. Hawaii Space Exploration Analog and Simulation. Volunteers live in a dome, isolated, for months, simulating a Mars mission. What do they learn? Isolation is hard. Even with other people, even with communication with Earth, being cut off, being alone, it's psychologically challenging. You don't even have other people. You're truly alone. That makes it harder, much harder. You need routines, structure, purpose. You need to keep busy, keep your mind engaged. You need to maintain hope. Even when things are hard, even when you're not sure if rescue is coming. Routines help. Wake up at the same time every day. Eat meals at regular times. Work on projects. Maintain your systems. Exercise, read, learn. Do something productive every day, something that gives you purpose. Purpose is crucial. You need a reason to keep going. A goal, something to work toward. Maybe it's improving your systems, making them more efficient, more reliable. Maybe it's conducting experiments, learning about Mars. Contributing to science. Maybe it's just surviving, day by day, week by week. You also need to take care of your body. Exercise is important. In low gravity, your muscles weaken. Your bones lose density. You need to work out. Stay strong. Stay healthy. Your body is your most important tool. You need to maintain it. Sleep is important too. Your body needs rest. Your mind needs rest. But sleep can be hard when you're stressed. When you're alone. When you're worried. You need to create a good sleep environment. Dark, quiet, comfortable. You need to stick to a schedule. Go to bed at the same time, wake up at the same time. Your body needs routine. And you need to deal with stress. Being alone is stressful. Being responsible for everything is stressful. The constant danger is stressful. You need ways to cope. Routine helps. Structure helps. Having a purpose helps. Working on projects. Solving problems. Building things. These activities keep your mind engaged. They give you focus. They help you stay sane. Because rescue? That's uncertain. At best. Mars is far from Earth. Really far. At its closest, Mars is about 34 million miles away. At its farthest, it's about 250 million miles away. That's a long way. Communication takes time. Radio signals travel at the speed of light, but even at light speed it takes time. When Mars is closest to Earth, a signal takes about 3 minutes. When it's farthest, it takes about 22 minutes. So even if you can contact Earth, conversations are slow. Delayed. Frustrating. Imagine trying to have a conversation. You send a message, wait 3 minutes, or 22 minutes, get a response, wait again. Send another message. It's like talking through a very slow mail system. You can't have a real-time conversation. You can't ask quick questions, get immediate answers. Everything takes time. Everything is delayed. But communication is still possible. Mars rovers communicate with Earth every day, using radio antennas. Using the Deep Space Network, a system of large radio antennas around the world, in California, Spain, Australia. They track spacecraft, send commands, receive data. It works. Even across millions of miles. You could try to contact Earth, if your communication equipment still works, if you can repair it, if you can power it. You could send a signal, let them know you're alive, tell them your situation, ask for help. But help might not come. Not quickly, not easily, not at all maybe. But at least they'd know. At least you'd have tried. At least you'd have that connection, that link to home, even if it's slow, even if it's delayed. Even if it's frustrating, it's something, it's hope, it's a lifeline. And getting to Mars, that takes months, 6 to 9 months typically, with current technology. A rescue mission would need to be planned, built, launched, travel to Mars, land, find you. That could take years, if it's even possible. There are launch windows. Times when Earth and Mars are aligned. When it's easiest to travel between them. These windows come every 26 months, so if you miss one, you wait. For over 2 years. For the next one. A rescue mission would need to be designed, built, tested, launched, travel to Mars, land safely, find you. That's a lot of steps. A lot of things that could go wrong, and even if everything works perfectly, it could take years. 3 years, 5 years, maybe more. So rescue might not come. You might be alone, forever. You need to accept that. You need to build a life. On Mars. Using science, using your knowledge, using your determination. But here's something to think about. You're not just surviving, you're pioneering. You're doing what no human has done before, living on Mars. Long-term. Permanently, maybe. You're proving it's possible, that humans can live on another planet, that science can make it happen. Future Mars colonists will study what you did. Learn from your experiences, your successes, your failures. You're writing the manual, the guidebook, how to survive on Mars, how to thrive on Mars. You're making history, even if no one ever knows. And that's something, that's purpose, that's meaning, even in isolation, even alone. You're part of something bigger, humanity's expansion into space, the next chapter of our species, and science is making it possible. But here's the thing. You're not the first to face impossible odds. Humans have survived in extreme places before. In the Arctic, in the desert, in space, on the International Space Station. For months. Years even. And scientists are planning, right now, to send humans to Mars, to live there, permanently. They're designing habitats, life support systems, food production. Everything we've talked about, they're making it real. Elon Musk wants to send 1 million people to Mars. NASA is planning missions. Other countries are too. China. The United Arab Emirates. Mars is the next frontier, and humans will go there, will live there, will thrive there. Maybe you're the first, the pioneer. The one who proves it's possible, who shows that science can save you, that human ingenuity can overcome anything. Or maybe this is all just a thought experiment. A way to explore science, to understand chemistry, physics, biology, to see how they all work together, to appreciate how powerful knowledge can be. Either way, the science is real, the challenges are real, the solutions are real, and that's what matters. Science isn't just facts in textbooks. It's not just equations on a board. Science is a way of understanding the world, a way of solving problems, a tool, the most powerful tool humans have. On Mars, or on Earth, science can save you, it can help you survive, it can help you thrive, it can help you build a future. You just need to understand it, to use it, to never give up. So we've come to the end of our survival adventure. We've explored Mars, we've faced its dangers, we've used chemistry to make water, to create air, we've used biology to grow food, we've used physics to generate power, we've seen how all of science works together, to keep you alive, to help you survive. But this isn't just about Mars, this is about science itself. About how powerful knowledge can be, about how understanding the world around you gives you power to solve problems, to overcome challenges, to survive, to thrive. Science is everywhere, in the water you drink, in the air you breathe, in the food you eat, in the light that powers your devices. Science is life, and life is science. Think about it. When you turn on a light, you're using physics. Electricity flowing through a wire, creating light. When you cook food, you're using chemistry, heat causing chemical reactions, transforming ingredients. When you breathe, you're using biology, your lungs exchanging gases, your blood carrying oxygen. Everything is science. Everything is connected. Science isn't separate from life. It's part of life. It's how life works, how the universe works, how everything works. When you understand science, you understand the world, you understand yourself, you understand your place in the cosmos. And that understanding is powerful. It gives you confidence, it gives you capability, it gives you the power to solve problems, to overcome challenges, to survive, to thrive. Whether you're on Mars or on Earth, whether you're stranded or safe at home, science is your tool, your guide, your way of understanding and interacting with the world. So keep learning, keep exploring, keep asking questions. Because every question leads to answers, Every answer leads to more questions. And that's the journey. That's science. That's life. Maybe you'll never go to Mars. Maybe you'll never be stranded anywhere. But the science you've learned tonight, it applies everywhere. On Earth, in space, in your daily life. Understanding how things work, how chemistry creates and transforms, how physics governs energy and motion, how biology sustains life. This knowledge is powerful, it's useful, it's beautiful. And understanding science helps you understand the world. Why the sky is blue, why plants are green, why ice floats, why the sun rises. Everything has an explanation. Everything follows rules. And when you understand those rules, the world makes sense. It becomes less mysterious, more wonderful. Science isn't about memorizing facts. It's about understanding how things work. It's about asking questions, finding answers, testing ideas, learning from mistakes. It's a process, a way of thinking, a way of exploring. And maybe, just maybe, humans will live on Mars one day. Maybe you'll be one of them. Or maybe your children will be. And when they go, they'll use the same science we've explored tonight. They'll make water from ice. They'll create air from carbon dioxide. They'll grow food in Martian soil. They'll generate power from sunlight. They'll build a future on another world. That future is coming. Science is making it possible. Right now, scientists are working on it, engineers are designing it, astronauts are training for it, Mars missions are being planned, habitats are being designed. Life support systems are being tested. It's real, it's happening, and you're part of that story. Because you understand, you know how it works, you appreciate the wonder, the beauty, the power of science. And that understanding makes you part of humanity's greatest adventure. The journey to the stars. The expansion into space. The future of our species. So thank you for joining me on this adventure. Thank you for exploring, for wondering, for learning. Science is a journey, and you're on it. Every day, every moment, learning, growing, discovering. The universe is vast, full of mysteries, full of wonders, and science is how we explore it, how we understand it, how we become part of it. So keep wondering, keep asking questions, keep learning. Because science never sleeps, and neither should your curiosity. I'm Sleepy, and this was your science story for today. Sweet dreams, and may your curiosity never sleep.